So we got all the way through the we're in the 70E. So what does 70E cover? A lot of people think it covers electrical shock, electrical yeah, electrical shock, arc flash, and arc blast is the three major things that it covers. And we looked at some videos. So we looked at what basically causes improper training, improper procedures, dropping tools, accidental contact with electrical system, insulation failure, inadequate short circuit ratings, and voltage testing with inappropriate equipment. Then we move on. Buildup of dust, corrosion, and insulating surfaces, improper maintenance, sparks produced during racking of a breaker. And we understand what racking a breaker is now, right? Replacement of fuses, closing into faulted lines, and inattentive or overconfidence. And that last one is a big one. I think this is exactly where we're at, right? Racking a breaker, we showed that video already. So what's racking a breaker? Well, technically, racking a breaker is installing a breaker. That's basically installing the breaker. So even if your house, when you open up your panel box and you push that breaker into those blades back there, that's the same thing, except on these industrial breakers, you're dealing with what? Big ones, right? You understand. And like I said, these things are usually on inside a box, and they're on rails. You roll them in, and then when they rack them, they actually have some type of screw mechanism where they rack them in. We watched that. Qualified persons, we already looked at this. And this is basically the same one, the same explanation that they give inside the OSHA 1910, right? One who has the skill and knowledge related to the construction and operation of electrical equipment and installation, and has received safety training to recognize and avoid hazards, the hazards involved. And what's a hazard? Yeah, anything that has the potential to cause an injury, we call that potential. May be considered qualified with respect to certain equipment and methods, but still unqualified for others. So, in the Navy, we call it qualified. So you might be qualified to do this, but you might not be qualified to do that, right? You understand? So when I worked on my airplanes, I could do a lot of stuff, but I wasn't qualified to start up the engine until later. They qualified me in that too. But so you had to be qualified to start up the auxiliary power unit. If you wasn't qualified, you wasn't supposed to do it. But if you did it and something happened, then you'd be in a world of trouble, right? Qualified persons understand specific electrical hazards, knowledge of the construction and operation of the equipment, identify and understand the relationship between electrical hazards and possible injury, distinguish exposed live parts, be able to determine voltage of live parts, understand and complies with arc flash and shock hazard boundaries. This is a big problem that we have with people using test equipment to see what's there, instead of using test equipment to verify what's there, right? So what they're saying is that before you put a meter in a circuit, you need to know what you expect to see. And if you know what to expect to see, then you know if you got a meter that's rated 1,000 volts and you're going to try to measure 2,300 volts, you better not put the what meter in there. Because meters blow up on them. They will literally blow up on them because they're sealed units. And if you overdo them, you got expanding heat, it starts short circuiting inside the meter, and it's got no place to go. So what will it do? It'll blow up on them. And then you create arcs, and then you got big problems. Proper use of precautionary techniques, qualified persons, PPE, and what's PPE stand for? Personal protection. Insulated tools demonstrate how to select and use voltage meters, decision-making processes used to determine the degree and extent of hazard. So there's a lot that goes wrong along with meters now. Used to, when you got a meter, you would determine, you just looked at the highest range the meter would measure, and then you would come in and you would say, okay, you know, the highest range is 2,000 volts. That means I can measure 2,000 volts. But what they understood later on is that the electrical power that we have is not, if it says 2,000 volts, the problem is a lot of time we get these surges. You actually see these at your house. When something happens, you see lights get real bright for a second. Well, or some of them actually blow out, right? You understand? So we get surges on these power lines all the time. So since we get these surges, what they've done now is they've started rating meters not only on how much voltage, the highest voltage that they can measure, but also how much surge they can handle coming into the meter. So what they came out with is they came out with meter categories, and we'll look at this later on in a little bit. So what we do is we come up and we look at the meter, and somewhere on the face of the meter, it'll come up and it will tell us everything we need to know about what this thing is rated at. Now, usually when they put the ratings down toward the bottom of the meter, as soon as I get rid of this, just pause. What we do now is we rate meters in categories. So I'll show y'all later on, but down at the bottom of this meter, in fact, I'll just pass it around and I'll put it up on the video later on. This is a category 2 meter, category 2, and a category 3 meter right here. Now what the category displays, it tells us how much surge. What we'll do later on, I'll show y'all a chart that shows you that. So where was we at? So this is a qualified training, proper use of precautionary techniques, PPE, arc flash, right? Insulated tools demonstrate how to select and use a voltage meter, decision-making process used to determine the degree and extent of hazard. Okay, we'd already talked about that. Energize electrical conductors and circuits parts to which the employee, so this is justification of work. This is the actual section inside the 70E. We don't have the 70E standard, but we got, there's a book that shows 70E, but we've got a lot of information that tells us what it's on it. So, justification for work. Energize electrical conductors and circuit parts to which an employee might be exposed shall be put into an electrically safe work condition before any employee works within the limited approach boundaries to those conductors or parts. So what they've established, the 70E has established different boundaries that you can come into. And of course, the closer you get to the live equipment, or the closer you get to the work, the more PPE you have to wear, right? Makes sense? Unless the employer can demonstrate that de-energizing introduces additional hazard or is infeasible. Interruption of life support systems, that would be awful, right? So we got a life support systems. We're not going to de-energize those to work on, because if we do, we could do what? Kill people, yeah. A deactivation of emergency alarm systems. So we should never do that. Shutdown of hazardous locations, ventilation systems. circuit and conductors that operate at less than 50 volts. So we don't have to make the circuit electrically safe if it operates according to 70E if it's at or below 50 volts. Does that mean 50 volts won't kill you? No. You still have to make sure that you're safe around those voltages. You have to understand when you hook your meters and stuff, you still have to make those precautions and make sure you have it on the right scale. In EET 100, we blow fuses in meters all the time. Now, how do they blow the meter? Well, DC is about that too. We have problems with, this is when they're learning how to measure current and they're learning how to measure voltage. So what they'll do is they'll measure current, and then they forget to set up their meter to measure what? Voltage. And they'll leave it on current. Now on current, people don't understand this, so when we got our meter on voltage, it's got an extremely high resistance. Most meters, this meter right here is over 10 megohms when we got it on voltage. And other people don't understand, meters have resistance. So they're not infinite resistance. So you need to understand that too. But 10 megohms is a lot, right? You understand? But if I got into 1,000,000 volts, 100 megohms, the meter would blow up, right? You understand? Because it's pushing current through resistance, right? You understand that? So this guy here's most of the time when we measure these guys, and you can measure the input resistance of your meter. You can just take another meter and put it on ohms, right? You understand? And then hook it across this and put it on volts. And you can measure the resistance of this meter. This meter usually measures around 11 megohms. When I put it on amps, it's got almost 0 ohms between the two leads because we're flowing current through the meter. So we want the meter to have almost no effect on the circuit. If it had a big R on ohms, then it would drop voltage, right? You understand? We don't want our meter to drop voltage. So basically, when you put this meter on amps, it is a short circuit. If you put it across something, what did you just do? You shorted that sucker out. If you put it across the circuit, then you just created a short circuit, which is bad. So these things are fused, but you got to understand fuses don't act instantly, right? You understand? And all it takes in a high voltage circuit is just a little arc. That's all it takes. And it could do what on it? It could cascade. Because arcs create ozone. Ozone is a low path for current flow. You create an arc across your two junctions, then you got a big problem. So understanding how to set this meter up is very, very important. If you put it on ohms and you put it in a circuit, when you put it on ohms, it becomes an actual voltage source or a current source. So you're pushing current back through something that's trying to put out current. You could turn into a big problem, right? You could blow up your meter, or the meter, you could have problems. So understanding that range, what you should put this meter on before you put it in the circuit, you should double check that. Verify it before you put those leads in there that you got it on the right what? Right units. When you're measuring volts, you got to put it on volts. When you're measuring resistance, you got to put it on ohms or resistance, right? When you're measuring current, you got to put it on amps. Because if you have it the wrong setting, if you have your meter set up wrong, what could you do? You could blow it up in your hands, yeah, and kill people, right? Or have big problems. So you got to be real careful, even on 50 volts, to verify your meter. In our classes, we're dealing with very low voltages in most of our classes, except when you get into motor controls, and you could cause big problems. Justification of work, other work that may be performed within the limited approach boundary or exposed energy, electrical conductors or circuit. What can we do? So this is a little different. So this is where we come into play. So we can work on energized equipment. Only when we do what? Testing and what? Troubleshooting. So this is where we can cause problems. Now, if we do maintenance on it, we're supposed to usually lock it out or de-energize it, right? You understand that? And that depends too. So there's some maintenance, minor maintenance that sometimes you can do, right? You understand? the primary maintenance that we do when we remove and replace parts, then we need to de-energize that thing. But we're going to have to leave it energized when we do what? Troubleshooting. There's a question in the motor controls book on safety that says when you test for voltage, is lockout and tag out required? You'd be surprised how many people say yes. That's false, right? If you lock it out and tag it out, then you're going to de-energize the voltage and it's not going to do anything, right? Right. Safe work practices, de-energize, and the lockout policy, we'll look at that. Don't wear conductive what? Apparel, so we don't let y'all wear synthetic clothes in this class, because that's what? Yeah, and also it's flammable. Work area must be illuminated. We have really good illumination in here. Never reach into what? Blind spots. We got a video somewhere where a guy's trying to get into something. Don't allow conductive liquids near electrical work or equipment. Use the buddy system. At US Steel, it was 500 bucks. That was their policy. But I don't ever remember working at US Steel by myself. The whole time we were I was an electronic repairman out there. I don't ever remember going out and working on something by myself. So it was always what? Two. A buddy system over 1,000 volt works in what? Pairs. Do not defeat electrical interlocks and use non-conductive ladders. I told you about our last electrical instructor that came up through Bell South, right? These are warning signs. This is our PPE, our flash labels. So we have labels that's supposed to be on equipment now that indicate what we need to do. It indicates what type of PPE we're supposed to wear. So this would be a warning label. Arc flash or shock hazard, appropriate PPE required, 9-inch flash hazard boundary. This basically is a calculation. I've seen the formula before, but I've never done it, where you actually calculate a certain amount of calories per centimeter. And then that would determine where your boundaries are, how close you can get, what PPE you have to wear the closer you get to them. Usually what they do is they identify these with different colored tapes or painting on the floor, which would indicate where you could walk. I don't know if you've ever been in a plant where they have places now identified where you're supposed to walk, right? They'll have walk paths. And if you get out of the walk paths, then you could get hurt, right? 400 volt shock hazard when covered, glove classes. So this would require, so what we're going to look at is all these different classes. And of course, if you didn't know it, then you could very easily go on the internet and find out what a class 0 glove was, right? Does that make sense? Limited approach is 42 inches. Restricted approach is 12 inches. Prohibited approach is 1 inch. That means if you don't have any business being around that thing, and the closer you get into these three boundaries. So what's our three boundaries? Yeah, but limited approach, restricted approach, and prohibited approach. These are supposed to be identified now when you get around these. Danger. No safe PPE exists. Energized work prohibited. So if you ever see this one, it means you shouldn't even get into this if it had what? If you had your PPE on. No safe PPE exists. Energized work prohibited. So if you see this, you're not even ever supposed to do work on this thing live. Are we okay? This is the ARC ratings, and we're just going to look at this. This is actually covers a lot better than we do. So this would be the risk. This is where we're in. We're in hazardous category Z. I'm sorry, 0. And this is where it would be on the classification. They calculate the calories per centimeter, right? And this number over here would determine what type of PPE would be required. That makes sense? This is the approach boundaries we've already looked at, right? And this is the way they're supposed to be, right? So we have three boundaries. We have what we call limited, restricted, and prohibited. I think they gave that wrong. These are the three boundaries. Qualified workers is responsible for ensuring physical barriers are in place and all approach boundaries are enforced during work. Does that make sense? You okay? Yes? I don't know if y'all can see this or not. You might can see it if you've got the PowerPoint up. But these are different color codes that they set up for these different boundaries. So what they require to do now are these people that make these protective clothes, they're supposed to color code these things that we wear, right? Understand? So we're in 0. That was well below 0. And the only thing we're supposed to be able to wear is rubber gloves. And they should have a what color? Can you see that color? Beige, yeah. And this would be the colors for class. We're in 00, by the way. Class red, class white, yellow, green, and then orange means that's the bad stuff, right? We're okay? Voltage rated gloves. First line of defense, choose the right size. Leather protectors must be worn over the rubber gloves in some situations. So sometimes, and that's not, I told that. Some of them require rubber gloves. So what's the problem with rubber gloves? They what? Yeah, you do sweat in them, but that's, the problem is rubber's usually pretty easy to tear, right? You understand? So this is why they require what? Protection over them, which would be a leather glove. So just about all the rubber gloves requires you to wear leather gloves over the rubber gloves. Choose the right size. Leather protectors must be worn over rubber gloves. Gloves must be tested before first use in every 6 months. We had a company, I don't know if it's still out there, it was on Lorna Road, I can't remember the name of the company. But they made a lot of high voltage test equipment, and they actually tested, this is one of the things they would do, they would test rubber gloves. And it was really interesting that they'd have a big old water vat, and then they'd fill the gloves up with it, put it, and then they'd dip it in there, and they'd put electrodes between 2 of them, and they'd measure the current flow through the glove. It didn't meet a certain amount of standard, they would do what? They would reject them and throw them away. That was one of the things that they did. So you're supposed to be able to check these things every 6 months. If tested but not issued for service, gloves may not be put into service unless tested within the previous 6 months. Check before use. A roll-up test, inflator test. What is an inflator test going to do? Blow it up and look for leaks, right? You ever seen people do that? Huh? Blow the rubber gloves up and then check for leaks. And then the Salisbury test. I should have found the video. This is the one that we were talking about, where they actually immerse it and check the resistance of the layering. Outer layers must be flame resistant. Under layers must be what? Non-melting. Fit clothes shall be fitted properly loose without, I don't know what they mean here. Normally, if we're going to work around any type of moving machinery or gearboxes, we don't want loose fitting clothes. And in fact, a lot of companies won't let you wear won't wear your long sleeve shirts when you're working around moving machines. Because what? We had an instructor, this is back a long time ago, when, of course, now when you look at videos, these CEOs and stuff, you know, they used to always wear suits, but now they wear what? Blue jeans, yeah, they'll be up on stage. Well, when I came here, your instructors wore shirts and ties. And we had the instructor, Mr. Tate, he was a smart man. He taught all the calculus courses, but he was an electronic instructor. He taught the motor controls. Mr. Tate, we had a motor spinning in there, and Mr. Tate had his tie on, and it was a tie. It was a tie. And he leaned over that motor, and guess what happened? His tie got caught in the shaft of the motor. And luckily, Mr. Tate had his hands like this, and he locked his elbows, and it tore that tie The tie didn't choke him; it tore that tie off his off his uh, off his neck, which is funny. We laughed about it, but it wasn't. It could have been really bad because it could have hung him, right? But, so loose fitting clothes around moving machinery is not good. In fact, in the Navy, we had dog tags, but anytime we went out and worked, we were supposed to take our dog tags off because dog tags were what? Metal. And even though you wore them under your shirt, if you leaned over, they would come falling out. And we were supposed to take our dog tags off when we went out to work. Coverage. Clothing must cover potentially exposed area, your wrist and your neck. Care maintenance. Inspect before use. Laundry according to manufacturer's instructions. Especially when you've got flame retardant clothes. A lot of times they get their flame retardancy from a coating that they put on there. And you take those things and you put it in all this Clorox and stuff, right? You understand? And you put it in scalding hot water. What could it do? It could literally wash the flame retardant off. So what you need to do is make sure you read those instructions just like you do on just about all clothes you wear. So usually when you buy clothes, it's got a label in there that tells you what. How to wash them, right? Wash in cold water, or use this, use that. Well, this will be the same thing true here. PPE hazardous. So this is basically category Z, 0. We're in a double 0. This is what we should look at. 100% cotton, long pants, which we require. Safety glasses, we require. Hair protection, we don't require. We don't use leather gloves over here, or leather work. But we don't let y'all wear what? We don't let y'all wear shorts in here, right? Everybody okay? But what you need to do is make sure you follow the requirements for wherever you go to work. So this is basic right here for just about every place you go to work at, right? This is between calories 1.2 to 1.4, hazardous risk category 1. A 4+ cal long sleeve shirt and long pants. So now you have to get a shirt and clothing that's rated at certain things, right? Hard hat, safety glasses, arc rated face shields, hearing protection. What is VR gloves? Voltage rated gloves, I'm sorry. Leather gloves and leather work boots, right? Okay? This would be category 2, which is basically the same. It looks the same, but notice what's changed. Yeah, the clothing or shirts that you wear, right? They have to be now rated at 8+ calories, right? Long sleeve shirts, long pants or coveralls, hard hat, safety glasses, and the rest is the same. Are we okay? This is category 3, which is between 8 and 25 calories per centimeter squared. 25 plus flash hood over long sleeve shirts and long pants, safety glasses, arc flash rated face shields, hearing protection plus inserts. We didn't say that a while ago. So hearing protection means you have the hearing and then you have inserts in your ears, right? Voltage rated gloves, and leather work boots. This is PPE hazard category 4. This is where we start getting into the bomb suits, right? 40 plus flash with hood over FR rated sleeve, fire retardant, long sleeve shirts and long pants, safety glasses, arc flash hearing protection, voltage rated gloves, and leather work boots. And then that would be as high as we can go. And you ever see these guys put this on? Pretty tough. And the problem is, guys, these guys right here are hot. And they're very inconvenient to put on. So you have a lot of people to save, it's like people running lights to save 5 seconds, off their time. So anytime you don't put that on, and then you get killed, then of course if your company requires it and you don't do it, then it's not their fault, right? You understand? So if you tried to sue them or your family tried to sue them, then you're going to be out of luck because you what? You basically killed yourself. Now, this does not guarantee you're going to get killed, guys, but this gives you a really, really high probability of what? Of surviving. It's just like if you do stop at every red light, it still don't mean you're not going to get in a wreck, but your probability of getting a wreck drops down what? A lot. You know. So that's about it for this safety. We looked at the overall safety with the OSHA 1910 and then the 70E, which covers basically three things. What does it cover? Electric shock, arc. Sorry, y'all didn't see what I did. Good thing I don't record it. What covers what? Three things. What does it cover? Yeah, electric shock, arc flash, and arc glass. And then, of course, thermal would be usually the result of an arc blast, right? Okay. Any questions on that?
What was your PP?
Yes, still, we wore hard hats, and that was before the 70E came out. So we were under OSHA standards at the time. We wore safety glasses. We wore a hard hat anywhere we went. We wasn't required to wear long-sleeve shirts. So we wasn't required to wear fire-resistant clothing. We were required to wear long pants, right? And we were required to wear steel-toed boots with metal tarsal protection. Metal tarsal is the top of your foot. So we had to wear that. And that was it for the PPE. But you got to understand, this is in a time where when you walked in, basically you didn't have any safety training. And you came in as a apprentice, basically, and you worked for 6 months. And then if they didn't fire you within the 6 months, then they put you on what they call standard rate, which means now you was it. But what you did is they constantly had what we call SJPs, which was safe job procedures. And every time you came into work, you would have an SJP that you would have to go over and sign off for it. But I worked there for a long time, guys, and I don't know if I ever got through the SJPs, all the SJPs up there. But they had SJPs on how to use screwdrivers, how to use about everything, pocket knives and everything. But as far as the PPE goes, that was all we were required, no matter what OTs we were working. You know, we very seldom got in anything. Like I said, we were required to work with somebody anything over 500 volts. But like I said, the whole time I was out there, we never worked alone. We was always with a crew of at least two, sometimes more than that, depending on the severity of the problem. So that's a really good question, but now it's really, really changed, right? When 70E came out, and this has really, really changed what's required. And like I said, when we look at back at the first, when we looked at the number of accidents that we've had since 2003, it's dropped down quite a bit just because of what? Yeah, the 70E, basically, the 70E. Okay, so this is probably probably what they go through. So now when you go to work for you, I don't know. What I understand is that almost any place you go now, before they put you on the floor, they make you go through safety. Huh? Yeah, it's calories per centimeter square. So that's what they call it. How many calories how many burn off, and that's what they call it calories per centimeter square. Is what they refer to this calculation. And in every energy label has what they calculate, what they call a calories per centimeter square. The higher the calories per centimeter square, the more PPE you got to handle, and also that describes how far these limited and restricted and prohibited safety zones become. That's a really good question, but it's a math formula that they come up with as far as how much energy is available. So it all deals with how much voltage you're getting, how much current is going to flow, and how much current is allowed to flow into that circuit before the overcurrent protection devices kick in, and then also how far you're away from device. So the further you can get away from the distribution, the more safer high voltages are, because now you're dealing with the impedance of the resistance of the feed of how far you're away. So there's a lot that deals with calculating this. So normally most people that I've seen, they have people that specialize in coming to into your plant, and they will calculate in all the requirements and make all the measurements and do this for you, and then they give out the recommendations for what they recommend that you do. So yeah, in fact, we got a video where a guy talks about this, and that's what his company do. They come in and do that. But the formulas are out there, guys. I mean, you can go in and look at it. This is just the answer that you come up with. That's what they call it. So good questions. Any more? Well, what it deals with, it deals in energy level. So if I had a 600 volt supply that was fused at 1 amp, then I might be, you would have to wear leather gloves, but you wouldn't have to have rubber on them. So it all deals with how much energy can get to you when you get out there, understand? So it's a lot of math involved, and one of them is not only the voltage that you're getting into, it's also what the protection circuits are that deal with it, right? So like in a TV, when we had CRTs, there was over 35,000 volts on the anode of the TV, but there was no current available, right? So if that was true, if I came up there and touched you and I arc to you, we're dealing with thousands of volts when I have a static discharge. Do we wear leather gloves? When I walk around and get a static charge, do I put on leather gloves? No, because there's just not enough energy. There's no current available to that voltage. So as soon as I touch you, it discharges, right? You understand? So it would still be a category 00, right? You understand? So there's a lot involved with calculating this. So does 600 volts require level gloves? I would imagine in an industry environment it would, right? But in other applications it might not, right? If that makes sense. So I just can't, that's a question that odds are it would. But 240 volts might be required, right? If I have a watt, if there's enough energy. So if I have 240 volts fused at 200 amps, then I'll probably have to put on some PPE to work on that. Somebody wake up Anthony about that. Anthony gets off and comes straight here, so y'all gonna have to. Oh yeah, so this is what we was talking about. Fine, I got to put this up down. So this is the ratings, and later on we'll look at the different categories of these meters. But this has a Cat 2 rating at 750 volts AC. It's got a Cat 2 rating at 1,000 volts DC. And it's got a category 3 rating at 600 volts DC or AC.
So what are the estimation for?
This is just saying, this is where it's pointing you to it. Right? Understand? And then down here, these are the actual maximum ratings that we could have. So here's my amps. So this guy could get you in trouble because it's fused at what? 10 amps. When you move over to here, these guys are fused at 500 milliamps. 500 milliamps, by the way, is above the legal current through your voltage, through yourself, right? This is our meter common, and then of course this shows us the ratings on our voltage. So this says we have a maximum of 1,000 volts DC. By the way, this is the little symbol we use for DC right there. So anytime you see that solid line and those 3 little dash lines under that, that means that's DC. This is the symbol, that little squiggly snake line right there, that's the symbol that indicates this is AC. So this meter, if I go between this, the maximum I'm ever supposed to put on it is 1,000 volts DC or 750 volts for AC to stay within these categories. Does that mean it won't measure more? It might. But as soon as you go above these, then these categories are no longer available, right? Now what the categories do, the categories indicates how much of a surge the meter can handle. It's not the voltage range, but you'll have a different category at a different range, right? You understand? So this indicates how much surge it will. This indicates how much surge it can. You know, we'll look at that in I thought it was in that PowerPoint right there, but undoubtedly it's not. But it should be. So let's look at that while we're in here. Trying to figure out where it's at, but I'll need to go out and include this in even in this PowerPoint right here. Huh. I found my slide. This is the category of meters specified by IEC, which is the International Electrical Council, I think. This is an international organization. But OSHA has also a rating. I don't know if it shows the OSHA ratings or not. So basically the category of meter is determined by the surge rate on how far you're away from the distribution, right? So Cat 1 meter, these are usually for working on electronic equipment or equipment where measures have been taken in limits and transit those. So the further you get away from here, the more stuff that this surge has got to get through, the more likelihood, less likelihood it's going to have for it to get to you, right? You understand? It's just like, you know, if a lightning strikes out right out beside your house out there, probably blows lights in your house. But if it flashes 2 or 3 miles away, it's probably not going to hurt you because it's got to go through all these transformers and all these conductors. Does that make sense? So a Cat 2 meter, this is single phase. So this gives you the AC. Single phase, like appliances, PCs, TVs, and other households, located, outlets located 30 feet from a Cat 3 source, or more than 60 feet from the Cat 4. Cat 3, these are distribution levels, so this will get us right in here where it comes off our panel box right here, right? Distribution, fixed installation like distribution panels, short branches, and then Cat 4 would be on this side over here. So odds are we're not going to see many Cat 4 meters in here in electronics, right? If you went to work for some company like U.S. Steel or something like that, then you'd probably get at least a Cat 4 rating on some of your voltages. Does that make sense? And they're not the same. So some people think a Cat 3 meter rated at 1,000 volts would be good, better than a Cat 4 meter rated at 600 volts. So this is the chart, if y'all can read this, and this is the surge, guys. So a Cat 4 meter rated at 150 volts can handle a surge of 4,000 volts. Right? Y'all understand that? Cat 3 meter rated at 150 volts could only handle a surge of 2,500, right? Well, a Cat 4 meter, Cat 3 meter at 300, rated at 600 volts, y'all see this? Has nowhere near what a Cat 4 meter rated at 600 volts. So this could handle that watt. A cat 2 meter rated at 600 volts could only handle a surge of watt, 4,000 volts. A cat 2 meter could handle watt, 6,000 volts. A cat 4 meter could handle watt, 8,000 volts. So if it's got a 1,000 volt rating, so this is what they're going to rate right there. So 600 volts. I got a cat 3. This guy right here says it's a cat 3 meter up to 750 volts, which is not on my list. That would be somewhere between here and here. But a cat 3 meter, would be what? 6,000 volts. And this would be the amount of surge it's guaranteed to handle without doing what? Without blowing up in your hand. So a cat 3 meter is not equivalent to a cat 4 meter, right? You understand that? And we get people gets confused with that, right? So this is this meter. It's only rated at a cat 2 meter at above at what? Anything above 700 volts, right? AC, cat 2 at, now, why is it rated less than AC than DC? Anybody know? Why is it rated at a lower voltage for AC than it is DC? Right, but AC, what we have to understand is, let me bring up my other PowerPoint. Not that one. This one, and I'll insert something here. I'm not going to say this. So DC is a constant level. So DC, if this is 0, then DC is going to be, it's not constant, it don't have to be constant, it can fluctuate. But if I've got 12 volts DC, I've got 12 volts DC, right? AC does this. So AC we generate on what we call a waveform called a sine wave. And it just constantly repeats. And then this right here would be 0 volts. So what we do to get how much work we get out of this, so the work is constantly varying, right? So right here I would get 0 work. Right here I would get maximum work. But what your devices are going to do, it's going to average this out. Y'all understand that? So that means if I was looking at Alabama Power, these peaks right here are 170 volts. So that means between here and here, I have 340 volts. This is at my house. But my appliances don't see 340 volts, what we call peak to peak. It's going to see an effective voltage, right? You understand that? So what we do is we can't use an average because this, if I had 1 volt right here, I have a -1 volt right there, and those two guys would cancel each other out. So this is why when I take this meter, okay, I could do that meter, but I don't have the leads. So what I'm going to do is I'm going to come over here and put my meter on DC, which is this guy right here. And I'm going to come over here and let's make up my camera. I thought I was going to bring up a camera. Okay, full screen. Now this is an older meter, so this became out before they had categories. So this gives me my maximum voltages, but it doesn't give me a category which indicates how much surge this meter can handle, right? Understand? So what I've done is I've got my meter on DC. So that's the two, that's the symbol for DC right there, right? Okay. And I got it on the 400 volt scale, and I'm going to turn it on. And what I'm going to do is I'm going to come over here and put it in this outlet. And there's definitely power on this outlet, right? Understand? What's it going to measure? Huh? Okay, so I'm going to come over and put it in this outlet, and it's going to measure 0. Thank you. Why? Because this is an average of a cycle. The DC average of a cycle is 0. Why? Because your positive alternation and your negative alternation are canceling each other out. Okay. Now I'm going to go over and put this on AC. Now it measures 120 volts. Right? You understand that? Over here on DC, it measures what? 0. And this is another reason why you need to understand your meter. Because if you got your meter on DC and you go over there and measure a wall outlet and it measures 0, it's going to measure what? 0, and you're going to think it's what? You're going to think it's what we call dead. You're going to think it's energized, right? And you reach your hand in there and you get your butt shocked or hurt even worse than that because you didn't understand what's going on here. So DC, when you got your meter on DC, it gives you the average of what it sees there. So what they had to do is they had to come up with another method so we could get what work we get out of here. So the problem is my negative, we call it alternation. I get as much work out of my negative as I do my positive, right? Y'all understand that? So they came up with a method of calculating it. And they called it root mean square, which means we come over here and we take an infinite number of, on both alternations, we square it. What happens when you square a negative number? Comes positive, right? Loses the sign. Then we take the mean of that, which would be the average, right? You understand? And then we take the square root of that. And that gives us what we call the effective voltage. People shouldn't call it an average voltage. It's an effective voltage. And this is how much voltage, this is how much work a resistive load will do. So if I had 120 volts RMS across a resistor, it would do the exact same work as 120 volts DC. So all the voltages. So if they say 120 volts and it's AC, if they don't tell you it's peak, then this is RMS. That's RMS. Now, this is what we call a sine wave, which means it varies perfectly. So your positive alternation and your negative alternations are totally equal to each other. If they're equal to each other, then, or mirror images, then what we can do is we can take this peak voltage right here, which would be 170 volts, and then we can multiply it by 0.707. So if it's a sine wave, it is always 0.707. The root mean square will always be what? 0.707. So what's 170 times 0.707? Should be 120 volts. So this is, so 340 volts worth of AC peak-to-peak voltage gives us 120 volts worth of work. And this is what we got. Yeah, so 120. Now, the problem is if it's not a sine wave, so if it came over and looked like this, then I'm going to get work out of there, but the 0.707 don't work anymore, right? Because it's not the positive alternation and the negative alternations are not equal to each other. So some meters, standard meters, use 0.707. Then you have what we call true RMS meters. What do you think true RMS meters do? It actually calculates the root, the mean, the square. So true RMS meters cost a lot more money than just regular meters, right? Understand that. So they specify that on it, whether it's RMS or true RMS. If you're working in, I've seen people working for, electricians that brag about having a true RMS meter. What does that mean? They spend a lot of money for something they'll never use, right? Mean for mean. A mean is another term for average. So root means square, so it's kind of backwards. Root of, and basically it means the root, the square root of the average of the squares. If they don't tell you, it's RMS. So this scope, and this is the advantage of an oscilloscope over a meter. An oscilloscope don't average anything. It shows you exactly what's there. And the meter is going to do what? It's going to give you an average, or it's going to give you an effective voltage. On DC, it gives you the average. On AC, it gives you RMS, but it depends on the meter. I don't know if this is a true RMS meter or not. This is a fluke. If it's true RMS, guys, it usually has it on the meter somewhere. And that would be the difference between a $100 meter and a $300 meter, right? Y'all understand that? So, before you go out and buy a true RMS meter, you need to know what's going to require for you, because a true RMS meter, you know, would be like buying a iPhone X or whatever they call it now, and all you do is go on Facebook. I mean, all you got now is what? You got bragging rights. But what did you lose? You're going to lose a lot of money, right? Because most of your places now don't give these suckers away free like they used to. And what do you do now? You get a new phone. You have to pay. Yeah, you pay it. Yeah. So some of y'all might have a true RMS meter, but if you're working on like variable speed drives or pulse width modulation and stuff like that, drives, and you probably need a true RMS meter. If you're working on just standard AC circuits, then a standard meter will work fine, right? All you got to do is pay attention to your maximum ranges and also your category of the voltages you're going to get into. It don't mean your meter can't handle higher voltages. So you might have a meter that has that'll go up to 2,000 volts, but it's got a category 3 rating at 1,000 volts, right? You understand that? Then that means if you get above 1,000 volts, then you're not protected against surges anymore. Your meter could do what? Could blow up on you.
A little opposite. Why is on my mind? I had a motor. Let's go around the thing in the work. We didn't know at the time it was built for the same stop motor. When we go to the box, you know, the power box, you right both out. And then you go to the motor, you can hear it hum. It sounds like things like that. And then it said, like, we took the pound out, was about 6 volts, you know, off of the line, you know, right there in the motor. But when it did hit up like that, it said, what the voltage. I mean,
probably it couldn't. What happens is that a motor has two currents. Anything at rest wants to do what? Stay at rest, and anything at motion wants to stay at motion. So a motor pulls a lot more current when it starts than when it runs. So if you look at the nameplate, it says it's pulling 5 amps. Well, that's what we call the full load current. That's what it draws. That's what the motor should draw if it's running at its rated horsepower. If it's running below its rated horsepower, it's going to draw less. But a rule of thumb, but what they do is they'll put a code on it, and I'll probably try to give that to you. They put a code on the nameplate. It's required now that gives you how much over the full load current that motor should draw when you try to start it. Well, the problem is when it stalls, it's sitting there drawing what? Starting current. Well, see, there's something going on there because that motor should have been protected against that. So fuses, when you fuse a motor, you have to fuse it to allow it to start. So it's usually about 150% of the start current. So that way the motor will start without popping a breaker or blowing a fuse. So what's required on motors is some type of what we call overload protection, which means it's supposed to have something in that meter that will kick it off if it draws starting current over a certain amount of time. We call them overloads, and that's required. So that's what's strange. Single voltage motors usually have the overload they're supposed to have an overload inside the motor. If they don't have an overload inside the motor, then they're supposed to have an external overload on. So what was happening is you was hearing that motor try to pull starting current. And the fuses are not going to what? The fuses or the circuit breakers are not going to pop because they had to be rated to allow the motor to start in the first place. So motors are supposed to be overload protected. Anything above, good gracious, it's like a third of a horsepower. They're supposed to be overload protected, either internally or externally. Oh yeah, well what happens is you got windings that's magnetic windings, so it's got that really thin insulation on it, that laminated pane on there, because you got to get that magnetic coupling, and that stuff will burn off. So what you're doing is that insulation is in there to allow the motor to start, and it'll handle a certain amount of overload over a little while, but if you leave it on there, that motor's going to get extremely hot and it's going to burn those windings up. And then after that, the motors usually burn up. So odds are, yeah, it probably, and sometimes you get lucky, but odds are if you smelled it, it's not producing the horsepower than it's supposed to, because odds are it's got shorted windings in it. Got wrapped around it and stitched stuff. Yeah, but see, that's something's going on. Where was this at? What surprises me is why they didn't have overload protection on it. Well, see, the problem is that an overload protection will start tripping, and then if it keeps tripping, which means you're having problems with the motor, they'll go in there and they'll turn the overload up. Well, odds are, what we have now, most of our overloads now are electronic overloads, and they're just a little dial on the front of it, that if it starts tripping, what can you do? You can turn it up. Well, as soon as you do that, then you screw it up. So what's happened before probably is it probably tripped the overload and somebody went in there and set it up so it would run instead of replacing the motor. So and that's one big problem we have with belts, and we'll talk about that later on. Belts are really neat, and they're a cheap alternative to chain drives, and there's a lot of benefits to them, but belts can break. You know, it's more likelihood that a belt will break before a chain will break. And then they're loose, and then they wrap around things, right? So there's the categories, guys, and this is why normally when they rate these things, the AC voltage is rated less, because your surge is going to probably be riding above that upper pulse up there, right? So even though it says 120 volts, we've got 340 volts peak, but we're only looking at one side of it, 170 volts, right? Y'all understand that? So that's why AC is rated lower, because the surge could occur where? Could occur up there at the top, right? Y'all understand that? Okay, good. Any more questions? Good questions, guys. Even though that had nothing to do with the class. And we'll show y'all some overloads on the Amatro line. What they've done on the Amatro lines is they've got a lot of stuff on there that's not even being used in the PLC programs. But what they're trying to do is introduce you to just about anything that you could run into. It's on a smaller scale, but it's actually industrial rated stuff, right? You understand? And they've got overloads on one of their motors. So we'll go back and look at it